Right, so in this video we're going to look at a number of different types of radiation. We're going to look at alpha, beta, and gamma radiation. We'll look at a Segre plot, and this will probably take a couple of videos just to get through everything very specifically. So start out with alpha. So there's alpha. So an alpha particle, if you remember from GCSE, is just a helium nucleus. So helium runs around in the form 4 and 2, so that has 4 nucleons in its nucleus, 2 protons, and yeah, the difference between a helium atom and an alpha particle very specifically is the fact that we obviously write alphas in equations like that and not like this, because this is inferring we have a helium atom, whereas a helium atom has electrons around its outer, around the nucleus, whereas a helium nucleus does not. So as a result, what we're looking at here is a situation where we've got a helium nucleus specifically. So that's an alpha particle. Then we've got a beta particle. So a beta, or beta, or beta, depending how you want to say it. It doesn't really matter as long as you get it right and write it down right. So a beta particle, there are 2 types. You have a beta positive and a beta negative. So a beta positive and a beta negative. So beta negative looks like that because it has a -1, and a beta positive has a +1. Okay, so that's fairly easy to get your head around that. So those are the 2 different types of beta particles there. Now a beta particle is either, depending on each case, an electron, or in the case of the positive one, it's a positron. I'll let you work out which one's which. Hopefully you realize positive, and electron is negative, so it's this one right here. So electron is negative, positron is the positive version. I'm going to utilize these in very specific ways very shortly when we show you the Segre plot, which shows when these different ones are going to be used. And then finally, the third type that we need to make you aware of is gamma. So this is a gamma radiation. This is the same radiation that's in a EM spectrum. It's the same gamma that we always worry about as being radioactive. It is radiation, but it is pure energy in this wave. So it's just the electromagnetic gamma wave. Very high frequency, very high energy waves, okay, that form at the end of the EM spectrum. Okay, so before we go any further, we're just going to look at specifically these 2 and how these 2 are utilized in order to create a more stable atom. So we're looking to create a stable atom. So in order to understand this, you do need to have a basic understanding of the periodic table, and I'm going to show you something called a Segre plot. Segre plot. Okay, so this is a Segre plot, and effectively what this is telling you is that there is a number of atoms that reside on this belt of stability, and you can have a certain number of protons and a certain number of neutrons. So you have a certain number of protons and a certain number of neutrons, and what tends to happen is that when there is an imbalance of neutrons to protons, when something falls out of this belt of stability, then what tends to happen is it becomes neutron rich or neutron deficient, and so the neutron rich side is up. So obviously an atom that has a specific proton number is always that atom. So say for example carbon 12 would sit around here, and so anything up on this line would be carbon because carbon has a proton number of 12. And same with 20, 30, 40, 50. You just look at the periodic table and see what all these things are in that respect. Now, like I said, you can have a neutron rich or a neutron deficient situation. So I'm just going to draw on this picture here, and anything that kind of sits elsewhere. So say we have a proton number of 50, but it has too many neutrons. It sits outside of the belt of stability, and so it's still whatever 50 is on the periodic table, but it has too many neutrons. So as a result, we can predict that it's going to undergo beta minus emission. So this is beta minus. So this is going to give off a beta particle, otherwise known as an electron. Whereas something that is neutron deficient, so it has the same number of protons, it's still the same atom as before, but has too few neutrons, well, then effectively, you're going to have positron emission. Try not to worry too much about electron capture, that's just on this picture. We can talk about that in lesson. But positron emission is our beta positive radioactive particle, otherwise known as a positron, as we have here. So that's what happens when you've got too few neutrons and too many neutrons. But what happens if we just huge overall? So if we've just got a massive atom like up the top here. So all the atoms at the top here are absolutely huge and they have really high numbers of neutrons to protons. And actually it's the amount of neutrons that kind of creates that instability in this regard. But what happens in this circumstance at the top here is that we get alpha decay. And alpha, as we know, is giving off a particle, a helium nucleus, which has a mass number of 4 and a proton number of 2, which is very similar and is effectively a helium nucleus. So this is a very nasty, big, positively charged particle that is being emitted off of this to try and create some sort of realm of stability here. So we're going to give an example of each one of these in the next video, and where we can have a look at alpha decay, we can have a look at beta minus and beta positive, and then in a subsequent video we will just have a quick mention of gamma decay as well.